Hello everyone and welcome back. My name is Mr. Covalt, and in this video I'm going to be going over Vesper theory, and in a future video or in my next video I'll go over hybridization. I have gone over Vesper theory in previous videos, and in this video I'm going to go over it again, but I'm going to use a PowerPoint so I can show you some nice pictures and visuals that kind of help to see why molecules will have the shapes that they have. And um, so I want to begin by showing you this table. And I'll show you a few tables, and I'll point out some things in the table that are kind of important. Um, so again, the first thing is you have the you have these columns, and here you have electron groups and you have bonding groups. So these are the atoms that are actually bonded to your central atom, and then here are these lone pair groups, right? So or these are the electron groups, the total electron groups. So the total electron groups is both bonding and non-bonding, or lone pairs. So here you can see that lone pairs are 0, and the bonding groups, the number of atoms you have bonded is 2. So the total electron groups is 2. And so you'll see here that the shape of the molecule is linear, right? And so again, they have this distinction between electron geometry or electron group geometry and molecular geometry. And so the electron group geometry is taking in consideration the total electron groups, which includes the lone pairs. And so again, because there's 0 lone pairs, the electron group geometry is the same as the molecular geometry. And the molecular geometry only looks at the bonded atoms, the shape of the molecule, when you're only looking at how the atoms themselves are arranged. And so because there's no lone pairs, these are going to be the same. And so you have this nice picture here for the linear shape. And again, for these, if you have the electron groups, and again, this is also referred to as the steric number, right? The total number of electron groups bonding and non-bonding. And so you'll see here that you have two possibilities. You either have 0 lone pairs, and so you have all of your electron groups are bonding groups, and that gives you this trigonal planar shape. And it's called trigonal planar because you could see that they kind of form a triangle, and they're all in the same plane, so it's a flat molecule. So it's trigonal planar. But here, if you replace one of those atoms with a lone pair, and so now you only have 2 atoms bonding to your central atom, and you have one of those groups as a lone pair. Then if you look at the actual shape of the molecule, so here, like at the top of the molecule, they're not showing you, but there's a lone pair there, and that lone pair is bending the atoms away. So this is a bent shape instead of a linear shape. So this doesn't have any lone pairs. You got 2 atoms, but there's no lone pairs here, so it's linear. But you stick a lone pair in there, those electrons are going to repel the electrons in the bond, and they're going to bend away, right? So this is how you would use this table to figure out what shape you have. So if you know the bonding groups and the number of lone pairs, then you can figure out what shape it's going to be. And again, one thing about the electron geometry is no matter how many bonding groups you have, as long as the total number of electron groups you have are the same, then the electron geometry will always be the same. So for both of these situations, the electron group geometry is trigonal planar. And for these 3 situations, because they all have 4 total electron groups, the electron group geometry is tetrahedral. But because they have different numbers of lone pairs, the molecular geometry is going to be the same. The shape of the actual molecule is the same, and is going to be different. Excuse me. So these are going to be different shapes, and so you can see here that the shapes are obviously different when you're looking at the molecule. But if they were to put the lone pairs in, the shape would be tetrahedral for the electron groups. So all the electron groups would still have a tetrahedral shape, but the atoms themselves have a different shape. Okay, and so you can the table continues here as well. And so with these two, you have the d orbitals come in, and you get what is called the expanded octet. And again, it's the same thing. You get these different geometries, molecular geometries, but the electron geometry is the same depending on how many lone pairs you have. And so here's another table. So this is a different table, but same idea. And again, steric number here. This is on top is steric number, and that's the number of total bonding and lone pairs. So the steric number will be the same for all of these molecules. So here they're all bonded. You have 5 bonded atoms to your molecule, and you get a tetrahedral. You get a trigonal bipyramid. And then if you replace the one of those atoms with a lone pair, the electron group is still trigonal bipyramid, but the molecular shape is now seahorse or seesaw. And so you can see that going this way, you're just replacing the number of lone pairs, replacing the atoms with lone pairs. So what is Vesper model? That Vesper again stands for valence shell electron pair repulsion. We're looking only at valence electrons. We're looking at the orbitals of valence electrons. And so the valence electrons in that valence shell, those electrons are going to repel each other because they're all negative. And we're looking at groups. It says pair repulsion. I like the word group better because when we talk about double and triple bonds, yeah, technically um, each bond has a pair of electrons. And if you have a double bond, that double bond has 2 pairs of electrons. So that makes it confusing for students because we're talking about pairs and there's 2 pairs. But when we have a double and triple bond and we're trying to figure out the shape of the molecule, we treat the double and triple bonds as one group, right? So even though there's actually 2 pairs of electrons in a double bond and there's 3 pairs in a triple bond, we treat that as just one group as a whole, right? So when we're trying to count the number of groups around our atom, we would count double and triple bonds as one group, not 2 groups, not 3 groups, just as one group. So that's just a clarification on that. So again, the model here is that the shape of a molecule is due to minimizing the amount of repulsion. So giving electron groups as much space as possible is what the goal is for having a shape. And so that's the that's the reason for the shape. So if a molecule has a certain shape, it's because that is that's minimizing that gives the most I should say the minimal amount of um, repulsion between the electron groups around your central atom. So if we're looking at a picture here, here's your central atom in the center. And so you can see these 3 atoms are bonded. And so we have a bonded group here, we have a bonded group here, and we have 3 bonded groups. And these electrons in the bonds are all negative, and so they're going to repel each other, and so they want equal space. And so this is why this particular atom has a trigonal planar shape, and because this gives the most space to minimize the repulsions. So that's Vesper. That's the idea. And so here I'm going to go over a few shapes, and I'm going to kind of show you pictures that are really cool. So if you have a linear geometry, then you've got 2 bonding groups here, and so the bonding groups are going to repel each other as most as possible, as much as possible. And so to be as far away as possible, these atoms, these electron groups are going to be 180 degrees from each other. They're going to be opposite sides of the central atom. So that gives them the most space. So it gives it a linear geometry. And here's two balloons that kind of give you an idea. If we're thinking of this as, electron space or the electron clouds, right? So the electrons exist in a space, and so this is the space between the two atoms. Here's your central atom in the middle between the two balloons, and so the other atoms are kind of on the outside. And here you have your electron space, or your electron um, map. So you can see that the electrons are going to be on opposite sides of each other. Here's again a pictorial of a trigonal planar geometry. So again, I showed you this just a moment ago. So here you have 3 fluorines bonded to your boron, right? So this would be boron trifluoride. And so again, the electrons in the bonds want to be as far apart as possible. And so to get that in order to get that minimal amount of repulsion, they take the shape of a trigonal planar geometry. So you can see they're all 120 degrees from each other. That's as far as they can get from each other. Anything else is going to give you a smaller angle. And so this is the shape that you would have if you have 3 bonding groups, right? Here we have 3 atoms bonded to the central atom, and so this is the shape of that molecule. And again, you have the 3 balloons that show you. So you can see that the balloons are the electron clouds, right? You have the electrons are taking up space. Electrons are occupying a certain space, a probability, and so because they take up the space, they're pushing each other away, and you get this triangular shape here. So the balloons are a nice analogy for the space taken up by electrons in each group. Again, here's the tetrahedral, and so anytime you have 4 bonding groups or 4 electron groups, you're going to have a tetrahedral geometry around the central atom. And again, the angle between all of these is going to be 109.5, especially if they're the same atom bonded to your central atom, then they're all going to have the same angle. If you change the atoms, if one atom is bigger than the others, like if I replace one of these with an oxygen, which is tends to have more electron density, it might take up more space. Or if there's a double bond, we'll talk about that more later. But the take home point here is if you got 4 electron groups, they're going to arrange themselves to minimize repulsion, and that ends up giving you your tetrahedral shape, and that's 109.5 degrees here. So again, if you have 5 groups around your central atom, they're going to arrange themselves in a way to minimize the repulsion. And so in this case, you have 3 groups around the plane. You got this trigonal planar shape in the middle here. And so that's giving them a 120-degree angle between the atoms here. And then you got on the axial position. So if you're thinking on the axial position, you have the top and the bottom. That's a 90 degrees. And so this allows for the minimal repulsion. And you can think of this as like the Earth. The central atom is like the Earth, and you've got the poles, right? You got the axes of the Earth, this north and south pole. So you can remember that that's why we call these the axial position. And so you could think of these as the north and south pole. And then these, if this is the Earth, and on the equator, these 3 atoms would be bonded along the equator, divided or spread out at 120 degrees. So that's why we call them the equatorial position, or equatorial chlorine. So the equatorial position gives you a 120-degree angle of space, and then the axial gives you 90 degrees. And so this, if you have 5 atoms or 5 bonding or 5 groups around your central atom, you're going to have a trigonal bipyramidal geometry. And finally, you have your octahedral geometry where you have 8 complete groups. So you have your sulfur hexafluoride, and you got 6 fluorines bonded to your central atom. And so all of these are going to be 90 degrees. So there's just no way to get it give any more space. So all of them have a 90 degrees angle between them. And so we call this octahedral geometry. Okay. And so here's a picture of what the octahedral geometry looks like using balloons again. So again, I think the balloons kind of give you a visual of the electron density, right? So electrons take up space. Remember, you have these probability maps, these orbitals, and so you can think of the balloons as being the space occupied by the electrons. And so you can see here that this octahedral space allows these balloons to have the most space possible, and so that's like the electrons repelling each other, and I think it's a nice analogy. Okay, so what are the effects of lone pairs? Now we need to talk about lone pairs really quick. So lone pairs are different from bonding pairs. So if you have electrons that are being shared between atoms in a bond, that kind of stretches the probability map, the space taken up. So if you think of a balloon and you stretch the balloon, it starts to narrow and takes up less space. And so bond pairs of electrons that are in bonds that are bonding two nuclei together, and they're being shared and they're attracted to both positive nuclei. That's going to make them take up less space. A lone pair is not being shared with any other atom. It's on the central atom or on some other atom, but they're not being shared, and so their space is going to be the space that they take up is going to be larger, and so they're going to need more space, and they're going to repel more. So this is going to affect the bond angles, right? So if you have a lone pair that wants more space compared to a bonding pair, like a pair of bonded electrons, that's going to push more uh, against the bonding electron groups, right? So that's going to make the bond between the atoms get smaller, because if you have a lone pairs needs more space. It's pushing the bonded pairs, pushing the atoms more, and so it's going to push them closer together, and so that's going to create a smaller angle. So the relative size of the repulsive force interactions is as follows. So the lowest repulsive force is going to be where you have bonding pair and bonding pair, right? So you have a bonding pair of electrons where they're being shared between two atoms, and you have another bond with another atom, and so both pairs of electrons are being shared, and so they don't take as much space. So that's going to be the lowest repulsion that you have. Medium is going to be where you have a lone pair and a bonding pair next to each other. So if you have a lone pair, that's gonna create more of a repulsive force. And then the highest would be if you have two lone pairs, right? Because both lone pairs want more space. So if you have two of them, then that's going to be a much higher repulsive force. And so you can see that here in this example here. So the bonding angle, so if you have all bonding groups, so here on the left you have nitrogen with all four atoms bonded, and those are going to be equally distributed. The bond angle, as we saw, is 109.5. So all of the angles between the atoms is going to be 109.5. So it's got the ideal tetrahedral geometry. But what if you have a lone pair? So this lone pair actually is going to take up more space. It's going to be more repelling, more repulsive. And so it's going to push these three other atoms closer to each other. It's going to push them away closer to each other. And you can see that the bond angle becomes 107. So it's a smaller bond angle because the lone pair needs more space. It's going to be more repulsive. And so it's going to drive these three atoms away and closer to each other. So the actual molecular geometry of this molecule doesn't give you the 109.5 degrees. It's got 107. And what if you have two lone pairs, right? So same thing. The electron geometry of the oxygen is 109.5. So all electron groups, if these were all bonded atoms, then it would be 109.5. But if you take a molecule like water, water has two lone pairs on the oxygen. And so those two lone pairs are going to push even more against the atoms, and that's going to drive them even closer together. And so the angle is 104.5. So the actual molecular geometry angle is much smaller than the expected 109.5. And it's because you have these lone pairs. And the same or a similar thing would happen if you have double and triple bonds. Because you have more electrons in your double bond and more electrons in your triple bond, those are going to have more of a repelling force. And so if you have a double bond in your molecule, then that's going to repel and push the other atoms farther away and closer together. So, um, that's the bond distortion due to lone pairs. Okay, so that's it for this video. I hope you found this video helpful, and I hope it was a learning experience. If you learned something from it and you enjoyed this video, please like my video, hit that like button, please subscribe to my channel, hit that notification bell so you can notified by other videos. And please put a comment in the comment section. Let me know what you think, and if you have any questions. Thanks for joining me. Have a great day.